Hey guys, so I know semester is over in 2 weeks, which is a big bummer for everybody. I know for some people this is a relief because they've been stressed out with trying to handle, family stuff and with the virus and all that. So if you were, fortunate to be able to really spend time studying and you don't have any effect of the virus on your family and you're really confused as to why all of a sudden we would just cancel school, just kind of think about some of your classmates who might have a family member who's being quarantined because they have the virus, or maybe some people are getting full-time jobs to help their family financially. So I know this isn't necessarily the best for everyone, but best for each person, but it is the best for everyone. So just kind of think about, the other people around you and what they might be going through as to why the decision was made. But regardless of that, we're going to at least try to get through as much as 16 as we can. I'm not going to add any extra work. It's still going to be the same amount that you would normally do on a normal day. And we'll just get through what we can. And for those of you that would like the rest of 16 and 18, just contact me and I'll give you that info so that you can at least have all of the content that you would have got otherwise. All right, so 16 is about acids and bases. So this is a pretty popular chapter just because it's on stuff that you've already kind of heard about. We'll talk about the pH scale and those kind of things, but we're gonna get to it in a lot more depth than what you might be used to when you learned about it like in a general science class or something. So our little chapter beginning slide here is, I think this is an old Spider-Man comic or something like that. But so the guy on the left says, "Don't worry, Mask," which I guess the guy on the right's name is Mask. "Don't worry, Mask. This base will neutralize that acid." So I guess homeboy on the right got some acid in his face or something, and so he's gonna help neutralize it. And I like how the guy on the left is holding a ring, and it's supposed to be like a chemical compound. I guess they're trying to have benzene or something. I don't know what they're doing here, but that's our book chapter intro. You can read it in your book if you want for more entertainment. So let's talk about acids and bases. So there's some common acids. So here are the names of some common acids with their formulas and the uses and the strengths. We've already kind of talked about this a little bit, but I wonder when we talked about naming acids and bases before, last semester, but I want to just reiterate. Usually you'd have to memorize these names and formulas and the strengths, but since you get all your info with you on, well, we don't have a test, but on any other like homework and stuff, you don't have to. But if you notice, acids, they have a lot. So they can be explosives, and so a lot of people think of acids as being really bad because they can be, for cleaning, for glass etching, those kind of things. But they're also things that we have, like we have stomach acid in our stomach. So it's not, vinegar, soda water. So things that we would ingest. So some acids we can eat. Some acids are even safe enough that we'd be willing to put them in our eye, okay? So there's a lot of different uses for acids. So I don't want you to just get stuck on like acids are these things that will corrode your hand away and eat your bones and all this crazy stuff, okay? Which there are some that do that. And then just know that there's different strengths and weaknesses. Also remember, we talked about naming, all acids start with an H. Okay? So remember we talked about binary acids and oxyacids. So it's always H plus and then either a polyatomic ion or just a nonmetal. Okay? All right, some common bases. So here's the names, the formulas. Some of them have common names. So you've heard of like baking soda, ammonia, you might have heard of lye, and they have a lot of uses. So same thing, some of these could be stuff that we don't want to necessarily mess with, but then we could cook, we could digest some of them. We can even use some of them just to clean ourselves, okay? So lots of different options also with bases. So bases can be strong down to weak and then have a lot of different varieties. So how do we determine if something is an acid or a base? So we need some sort of definition. So that's where the Arrhenius definition. We're going to talk about two different definitions. We're going to talk about the Arrhenius definition, and then we're going to talk about the Bronsted-Lowry. So they just kind of talk about an acid or a base differently. One is going to focus on its formula. One is going to focus on its behavior. All right, so the Arrhenius definition is any substance which ionizes in water. So remember, ionizes means it breaks apart into ions. So this is saying any substance that I dump in water, when I dump it in water, it's going to break apart and create cations and anions. So any substance which ionizes in water to produce, if it produces protons, now when we say protons, I don't want you to think about like protons, electrons, neutrons. Protons here are going to be H+. So anything that produces an H+ is an acid. Anything that produces a hydroxide ion, OH-, is a base. Okay? Produces H+, it's an acid. If it produces OH-, it's a base. A better version of the Arrhenius definition is that acids have hydronium ions. This is H3O+ in water. Now what that means is when an acid releases this H+, it actually reacts with the water because it's in water and produces H3O+. So most of the time this isn't floating around, really it's the hydronium ion that's floating around. So a lot of times you'll see in like equations or whatever, H+ and H3O+ are like the same thing. So if you have H+ or H3O+, you can plug them in interchangeably into a reaction. Don't get overworked up about the difference between them, okay? A base is the same, it's those hydroxide ions. So if there's hydroxide ions in water, then it's basic. So you might have something like HCl. It separates into H+ and Cl-. So since there's H+, this is an acid. NaOH separates into Na+ and OH-. So since there's OH-, this is a base. So you might be asking yourself, well, NH3, why is NH3 basic if it's supposed to create an OH-? There's not even an O here for it to create an OH-. This is why we have two definitions. Sometimes the Arrhenius definition just isn't enough to explain all the different options for defining an acid or a base. So this is why we need a second definition. So our second definition is going to be the Bronsted-Lowry. And this is going to be based on how a molecule behaves. The first one, our Arrhenius, is what it's comprised of, what it makes. This is how it's going to behave. So, a Bronsted-Lowry acid is a proton, talking about H+ donor. So these guys are going to give up a H+. A Bronsted-Lowry base is going to be a proton acceptor. He's going to gain an H+. Acids lose an H+, bases gain an H+. All right, so let's talk about the NH3. We wanted to know why is he basic. So we've got a reaction. NH3 plus water goes to NH4 and OH-. So whenever we have a reaction like this, I like to figure out who's matched with who. So I have my NH3. So he needs to be matched with a partner on the other side. Okay? We're going to call this a conjugate, and we'll talk more about this in the next couple slides. So his partner would be NH4. So then water's partner has to be OH-. So let's look. If I'm going from NH3 to NH4, my option is either to gain an H+ or to lose an H+. So from here to here, do I gain or lose? I'm going to gain an H+. So if I gain the H+, I'm accepting it, so that means I'm a base. The water goes from here to here. He had two H's, now he only has one. So he's going to lose an H+. So if he loses, that means he donated it, so he's the acid. So what really happens in this reaction, what's really going on, is that the H plus goes from my water to my NH3, and then this is what it makes at the end. So we have a transfer of the H plus from the acid, because he's the donor, to the base because he's the acceptor. Okay? All right, so let's talk about strong and weak. Strong acids and bases almost completely ionize. And we talked about this when we were talking about strong and weak electrolytes, and when we talked about naming, we talked about strong acids and bases then, but we're refreshing. Almost completely. So if it's a strong acid or a base, how you know this is one, this guy, you could go back to your chart, and he's right here. You can find him in your chart, and it says he's strong. Or another thing that helps you know that he's strong is that he is a single-headed arrow, which means he's gonna pretty much completely go to products. So think about our equilibriums that we talked about last chapter. So he's not reactant favor. He's pretty much gonna go completely to products. Weak acids and bases do not fully ionize. How you know this is you have to figure out, is this weak? They're both on the chart, so you could look it up. But the other thing is this is a double-headed arrow. So if it's a double-headed arrow, that means you have a balance. It's not going to completely go to products. Some of the reactants are going to be left over. So you're kind of going back and forth with that equilibrium. Now, another thing to note is that whenever we go from my reactants to my products, the products are going to be a new acid-base pair, because you can look at it backwards. So same thing we did before. If I look here and here, that's his partner. That's his partner. If I look backwards, he would have to lose an H plus. If he loses the H plus, then he would be the acid. He is going to gain the H plus, so that means that he's going to be the base. So we can do it the same thing. We have an acid-base pair here, and now we have another acid-base pair here. Now let's talk about how they relate. Okay, how do these pairs relate? So these pairs are what we call, before I get to there, here's a picture of my strong acid and my weak acid. So if it's strong, so this guy's strong in case you can't read that, this guy's weak. So if it's a strong, this guy's HCl. You have a bunch of your hydroniums floating around, and then your Cl's are floating around. You don't have any HCl's floating around. Here, this guy is weak. So you got your cations, you got your anions, but then you have some of your molecules just floating around because it doesn't fully ionize. Okay? So that's the difference. This one completely, the strong completely ionizes. The weak, you're gonna have some of the ions and then some of the molecule left over. All right, so let's talk about acid-base pairs. So molecules are ions that are related by the loss of one H plus. This is the big important thing, one H plus, because an acid donates an H plus, a base accepts an H plus. It's only one H plus. So we can look here. To go from here to here, he has to lose an H plus. So if he loses, he's the acid, and that makes his partner the base. If I go back, I'm gonna gain an H plus, and so that's why he's the base and he's the acid. Okay? So we can have pairs like this. We can look at what's happening. If I'm an acid, I donate. If I'm a base, I accept. And then I can make my pairs. The difference is one hydrogen. One hydrogen is the difference. Okay? Now, let's look. Is NH4 plus and N2 minus, are these conjugate base acid pairs? So this guy has 4 hydrogens. This guy has 2 hydrogens. So the difference between them is how many hydrogens? 2. So these are not conjugates because this requires 2 H pluses. So for them to be a match pair, it can't be two H pluses. It can only be one H plus. All right, let's look at this. It says identify the base conjugate to HF and the acid conjugate to HCO3 minus. So I want to know his conjugate. Specifically, I want to know his base conjugate. Okay, so let's talk about what's going to happen. So we're going to look and find him a partner. So what is he going to do? He's going to separate. Okay, he separates. I've got my H plus and my F minus. We have to find him a partner. So the way that we find him a partner is don't look at the H, but look at the unique thing. So he's got an F, so his partner has to have an F. So to go from here to here, am I gaining or losing? I'm losing an H plus. So he's going to donate. He's going to accept. So he's the acid. He's the conjugate base. Okay? The difference, you might think, well, why can't I do the other partnership? The other partnership, the difference between this guy and this guy is an F. We can't have the difference being a element other than H. The difference between the two pairs has to be an H plus. Okay, other thing is it said that we were looking for his base conjugate. So if we're looking for the base conjugate, that means he has to be the acid. So now we want to know the acid conjugate to him. So that means he's a base. So another way you could think about this is if he's the base, I need his acid partner. What do bases do? Bases are H plus acceptors. So I need something that has another H. So if he's just H, I need to add, so I get H2CO3. So he would be my base conjugate. Or sorry, acid conjugate. Because he's the base, he accepts and makes my acid. All right, so then the other question, this little side question is, what would CO3 minus be to HCO3? So here's my HCO3. I want to know how does he relate to him. Okay, so if I go from here to here, am I gaining or losing? I'm going to lose an H plus. So if I lose an H plus, what does that make me? Makes me an acid. So that means he has to be the base because he's going to gain it. So that guy is my base conjugate. All right, we're going to practice some more. So here's just a different wording. These were in reaction, so you can visually see what's happening. These are not. So now I have to think about what's happening. So what is the conjugate base of HNO3? Okay, so I want the base. So if I want the base, that means he is the acid. And what does an acid do? It donates an H plus. So that means I'm going to lose an H plus. So I've got HNO3, I'm going to lose an H plus. So I'm going to have one less H. So I'll have NO3, one less H. But I have to also deal with this plus sign. You haven't had to do this yet. So far you've just had to pick out of the options. Like here you just had to pick the options or label it. So now we actually have to write it. I'm losing the H, so one less H, but then it's a plus. He's neutral. So think about what is 0 minus a positive 1? A minus 1. So that would be my base conjugate to my HNO3 acid. All right, let's do the next one. Well, I want the conjugate acid. So if I want the acid, that means he's my base. What do bases do? They're going to be a acceptor of H plus. So if I have O2 minus, I'm going to now add an H plus. So now I'm going to have an O and an H. Okay? And then negative 2 plus a positive 1 is a negative 1, or just a negative. So you have to do the elements and the charges. I want the conjugate base of this guy. So if I want the base, he's my acid. What do acids do? They donate H+. Okay? So if I donate it, I'm going to lose the H+. So I got to get rid of an H. So lose an H. This is a -1 minus +1, which makes it a -2. All right, next one. I want the conjugate acid of this guy, so that means he's a base. What do bases do? They accept H+. So I need him plus an H+. So I've got him plus an H, so that's going to be 2 H's. A -1 plus a +1 is just a neutral. So just him. All right, so those are my conjugate acids and bases. So we'll stop there. On the next PowerPoint, or next lecture, we're going to start talking about strengths. So how do I be able to predict if I have two different molecules? How do I know which one might be stronger or better? What are some trends for that? So we'll be starting that on the next one.